Okay, I guess, can I just start then?
Yes.
Okay, perfect. Okay, I'm going to be talking, my name's Anushka, and I'm going to be talking about joint work with my advisor, Irene Lowe, on dynamic contracting for payment for ecosystem service programs. So PES programs are when governments pay small landowners to conserve their land, and we can formulate this as a principal agent model where the principal commits to pay the agent based on some observed conservation level. The agent chooses a conservation effort based on their baseline ability and the principal's contract, and then the agent's efforts stochastically determines an outcome, and the principal pays them based on this outcome. Now, the trick is that the principal can't observe the agent's effort or baseline ability. So the question is, how should they pay the agent to induce them to take a high amount of effort? In practice, PES programs use conditional contracts where the principal pays the agent if and only if they meet some conservation threshold. So given that the principal's utility depends on the agent's conservation, we can ask whether the conditional contracts perform well and generate a high amount of payoff for the principal. Now, in 2022, Liash, Laghi, and Lowe found that this is generally not true because if we look at the ratio of the principal's payoff between the conditional contract and the optimal contract, we find that this ratio can be arbitrarily small. Now, the optimal contract is too complex to use in real life, but they find that a simple linear contract can achieve at least half the optimal contract payoff. And so one of the main drawbacks of this model is that it operates over one time period, which implies that once the contract ends, the agent no longer has incentive to put in any effort. So we want to develop a model where the agent can improve over time until they don't need payment to put in a good amount of effort and see what approximation guarantees a linear contract can achieve. So I'm including most of the main features from our dynamic model here. And the main one I want to highlight is that now we allow the agent's type to improve over time until it hits some optimal state where the agent no longer needs payment to maintain their land. And so we want basically the principal and agent to work together to maximize welfare. And so what we find is that period by period, the best linear contract achieves half the payoff of the optimal contract. And so this is similar to the static model. But we also look at the expected amount of time needed for the agent under each contract to hit their optimal state. And we find that the best linear contract takes at most twice as long as the optimal contract. And we can combine these results to by defining T to be the expected amount of time needed for the optimal contract to hit the optimal state. And we find that if we run the optimal contract for T periods and the best linear contract for 2 T periods, we can achieve a payoff approximation ratio of delta to the T over 2, where delta is the principal's discount factor in their payoff. And so this ratio makes sense because the half comes from the fact that the per period payoff is 1/2, and the delta to the T comes from the fact that it takes T additional periods for the linear contract to finish. So the delta to the T is like the worst case discount that the principal experiences. And so our results find that even in this more complicated model, the linear contract can generally achieve a good approximation ratio compared to the optimal. So I'm going to skip this slide because I think I'm out of time, but this is basically just the technical ingredients that allow us to prove our results. And yeah, that's my talk. Thank you.
Yeah, thank you for starting work. Thank you for the great talk. So now we can take a 1 minute break to just switch to the slide that I'm live. So sorry. Yeah, I guess we're good. So if you want to go ahead. Everyone, can you hear me? Thank you for sticking this long. My name is Abdullah, and I'm a PhD student in the IOR of Columbia. And today I'll be presenting my most recent work with Professors Rachel Cummins and Adam Mitchell. The underlying motivation, one of the underlying motivations can come from the 2016 elections, where if you look at the main polls, everybody was given Hillary Clinton to be the winner by landslide. But when you look at the result, the most unexpected, at least from their point of view, happened, and Trump was declared the winner. So the main problem was a huge mismatch between what people were expected and the actual results. Now, the question that we might ask is there a better way that we can allocate our surveying resources in order to make better prediction as to who is the winner? The challenges are that we can't survey anyone, so we have finite resources and we have to put these resources accordingly. But the second key challenge is that some states are unpredictable. We don't know the swing states prior to the survey process, and it is dynamic. So we don't know when to allocate, where to allocate, and by how much. So we're really going to approach this problem and many other estimation problems by an active learning framework that allows us to estimate multiple groups simultaneously, depending on the feedback we receive. So the setting, the mathematical setting is going to be the following. We have multiple distributions. Each distribution is unknown, has a given mean mu and a variance sigma. And we're going to look at it from this framework where if we have a policy E, pi, it's going to be sequentially, we're going to observe the feedback. That's going to depend on the distribution we've sampled. And then we're going to learn one additional sample. And this is going to allow us to select which group we're going to sample from next. And the difference with the state-of-the-art survey methods is going to be done dynamically. So this is a valid setting because the arms can be thought of as the unknown distributions. And the goal is to estimate accurately the means of all groups. Now, since this is a vector, we're going to need some sort of notion for this. So we're going to use the variance as a measure of accuracy, the variance of the vector. However, it's still a vector. So in order to convert it to some notion of amplitude, we're going to look at the norm of the variance of the vector. But this is highly random, and this is very complicated from an optimization point of view, since in the Venice literature, we only know how to optimize over additive, convex, nice structures. Yeah, so the benchmark is going to be the regrets, and essentially our paper is about the following contributions. We prove that the optimal regret depends on the structure of the underlying norm we study. For example, the optimal regret for the infinite norm is very different from the regret of more smooth norms like finite p norms. And we also show that our regret is tight in all the problem parameters, especially time, and the dimension of the problem, that is actually the number of groups here.
And I'm a PhD student at MIT. It's my great pleasure to talk about my recent work on group values in graphic design. This is a joint work with my PhD advisor, Dr. Doctoral Consortium, and my collaborators in the Paul and Preston. Our motivation comes from a recent line of literature that tries to use machine learning and optimization to improve the current refugee resettlement process. The problem can be abstract in a mathematical way. Essentially, you have a key online arriving refugee. Each refugee has a list of feature vectors. Based on that vector, they use machine learning to predict an employment score for every location. But location has capacity constraint. So in that sense, you need to solve an optimization problem in order to get the best employment score. They show that if you use this approach, you could lead to like up to 50% improvement compared to the status quo approach. The main message our paper tries to send is that if you try to use pure optimization, there may be a nature group bias concern. Let's look at this very kind example where we have two groups of people and two locations. One group basically has a very tiny benefit if you assign the group to the worst location. Then if you use the outcome-driven pure optimization approach, you will just send every person from the slightly beneficial group to the worst location, which is clearly unfair. So in our work, we try to operationalize group values in the dynamic assignment problem. Our framework incorporates the concept of minimum requirement for every group. Basically, we say the average score of this group should be lower bounded by 1. This something could depend on the sample count as long as it acts both feasible. And we do not impose our definition of growth and the fairness rule. We leave this decision to the policymaker. Based on our framework, we propose two algorithms with probably efficiency and fairness guarantee. The first algorithm is fair when outputs are large, but the second algorithm CVT can ensure fairness across outputs and the little loss in efficiency. We test our algorithm using data from Quantum Resettlement Agency in Netherlands and United States. The data show that the efficiency loss compared with the optimal algorithm due to group fairness constraint is actually quite small. But I want to stress that it is like the quality of data or this problem set, but not true in general, like from theory perspective. Yeah, thank you so much.
A little, but that's okay. In the interest of time, I have to keep moving. For instance, my name is not on the slide. I'll tell you what it is now. I'm Shayla Suresh. I'm a PhD student at the Yale School of Management, and I study operations, specifically operations that can help students and nonprofits. So today, I'll give you a little taste of some work I've been doing on studying the optimal timing for screening tests to identify students who have learning disabilities. Reading disabilities specifically. And this work is a close partnership with the Florida Center for Reading Research, where we got a lot of real world data, and with the Yale School of Medicine. So why are reading disabilities important? Why do we want to discover them? Well, reading disabilities are very common. In the United States, they affect 1 out of 5 students. However, the good news is that they're very treatable. They can be overcome with appropriate interventions, and already by law, any student in the United States who's diagnosed with a reading disability has to be provided with such an intervention by their public school. This sounds great, except that reading disabilities are very difficult to diagnose, to the point where 68% of students who have these disabilities are never identified, and those who are identified may be identified too late for these interventions to be effective. So our first research question is about optimal timing, but another issue is also that students from low socioeconomic backgrounds are significantly less likely to be able to access these intervention resources, even when they're performing equally poorly. So this question of disparity is a secondary question that we have. And obviously, the question I want to answer is a question of fair allocation in that case. So this work, the main contribution was actually to model this entire process, which you can imagine is very complicated and chaotic kind of system. We were able to show that the process for identification can be mapped into a simple diagram like this, which we can model as a time-dependent Bernoulli process. And importantly, we were able to calibrate every bit of this process using the real world data that we got from Florida's public schools, which covered over, the data that we have covers over 1 million students between the years 2003 and 2008. So just as a quick spoiler, we found that the main source of disparity is coming from the fact that parents and teachers can request for evaluations and interventions for their students directly, and parents from different backgrounds do this at different rates. So there's differences in identification there. The source of this optimal timing question comes from the fact that students are usually identified through these really quick, rapid, inexpensive screening tests, which are not super accurate and which get more accurate over time. However, the benefits that they get from this intervention get less accurate over time. So this became an operational trade-off, and we were able to show that the main lever that the school can really use is this timing, the question of when they're going to use these screening tests to give interventions to students. So we solved this problem for them. I won't go into any of the details here. Yeah, okay, so some of the quick insights that we were able to provide, we were able to actually work with stakeholders at all of the different levels of this this identification process. So to school administrators, we were able to provide them with an optimal timing policy. For educational researchers, we were able to give them some insights into the efficacy of improving the screening tests. Spoiler alert, there maybe should not invest so much energy into improving them. And then we have some insights to policymakers about different ways that they can change the existing identification process to significantly improve student outcomes on both of these efficiency and equity questions that I shared with you. So I'm out of time, but I'm happy to talk more offline. Please reach out if you have any questions.
Thank you. I'm Matteo. I'm going to talk about the paper React versus simulation of line lines leading to Oliver simulation on PhD student at Carnegie Mellon. So in this paper, we were interested in these line lines. These are small explosive devices that are left after wars ended in these territories, and they remain a threat to this war affected community for years. Not only for their physical harm from these communities, but also for the indirect development. And this, despite the efforts in the recent years, has continued to be a problem that is still used currently in ongoing conflicts, affecting nearly 70 countries and more than 60 million people. And the problem is that current military operations that seek to clear this land and return that to the people are very costly and laborious. There has been some previous effort to bring and to implement machine learning models to predict the land presence, but this basic limitation that we try to overcome in this work. So we propose this comprehensive pipeline to estimate the risk presence to a non-technical surveys. And non-technical surveys is the first step in a landmine release operation, where these military organizations, based on human expert knowledge and work for 20 years in the field, use historical island data, geographic information, local community surveys to plan some initial plans on how to approach these territories and intervene in these territories. So we're like, okay, we can actually formalize this and use a machine learning based system to help them prioritize and producing risk map to where they should go and intervene in these territories. And the pipeline is composed by three components. The first one is a data set encasement that integrates different sources of information into a data set for landline presence with rich relevant features coming from geographic information, social demographic variables and remnants of war indicators, and some historical alignment events. And we also argue how labels should be defined, rectifying the definition in the literature to model landline presence. We then fit this data set into a deep neural network model, where we design this deep tabular model with environment optimization to be resilient to distribution shifts and to be deployed out there, and also producing convincing global feature importance using this interpretable feature mask. Finally, the risk map generated presented with stakeholders through an interactive interface that present the model outputs to support the mining task the stakeholders. As you can imagine, our system consistently outperforms standard and current baseline across several relevant metrics. We are currently conducting a pilot fund study in Colombia with the United Nations Mine Action Service and some NGO Colombian campaign to ban landmines. That's the thing. And yeah, we're looking forward to leverage feedback from this pilot field test. Looking forward for large-scale deployments, including other countries. So follow me for more information.
Hi everyone, my name is Cindy Kim. I'm third year PhD student at Columbia University. Today I'm going to talk about pairs for the inclusion system. So first I want to ask this question. Do you think the inclusion systems such as Uber, Lyft, or supply system, factoring system, do you think these systems are fair? So we don't have enough time to discuss this, so let me share my contributions. So what I did is like I analyzed Uber dataset in Uber in Manhattan area. And I calculated fares per miles from Times Square to other locations. And here colors represent fares, and you can see that fares are depending on locations. I did similar analysis for access, and access is defined as the percentage of people who can use the system or who want to use the system. And again, access is depending on location, right? So my question is like, what if we make faster access the same or similar? Is it beneficial for everyone? Is it beneficial for somebody, or is it beneficial for nobody? So I adopted two fairness criteria. One is price fairness, and another is access fairness. Basically, you want to make the same or similar prices or access. Just think about two locations. And to measure the impact of fairness criteria, I introduced two metrics. One is consumer surplus. You can think of it like consumer happiness. For instance, blue customers at location one, they can be happier than before or less happier than before. And the second metric is like social welfare. This is for considering the impact on two stakeholders, including platforms and all customers. So this is defined as the revenue and plus total surplus. So when we try to make these similar prices between two locations, we could fully characterize four reasons in terms of the tendency of social welfare and customer surplus. For instance, in blue region, you can see that blue customers at location one, they can be happier than before, as well as red customers at location two, and social welfare increases. What about access fairness? I think this result is kind of interesting because when you try to make these similar access between two locations, and blue customers at location one, they're less happier than before, as well as red customers at location two, and social welfare decreases. So this is kind of a lose-lose scenario. And furthermore, when you try to make the same access across two locations, then the system should be shut down, which means that nobody can use the system. So for instance, let's say EAAMO'23 wants to distribute sour candy channel, because tomorrow is Halloween, in fair manner, then under the perfect access fairness, nobody can get the candy. And this is somewhat fair because everyone gets the same amount of the candy, right? So what I really want to say is like fair constraint in operation systems can have unintended or non-obvious consequences. So we need to think about the meaning of fairness criteria. If you're interested in my work, please visit my poster section. Thank you very much.
Hello, I'm Kenya Andrews, and I'm excited to share the work that I've been doing with Booth Nisa and with Ching, looking at intersectionality and testimonial injustice in medical records. Intersectionality is how all the parts of who you are come together and reveal how you receive power in the world. And testimonial injustice is when you say something, but somebody doesn't really believe you because of prejudices that they have about you. So it could come from several of those aspects, right? Now, previous work has shown that clinicians are more likely to ignore Black and female patients. And we also saw other works that biases can be hidden or not necessarily presented unless we look at intersectionality. So not all males are treated the same. Sometimes poor males are treated worse, sometimes Black poor males are treated worse, right? So it matters how all those things come together and present you to the world. We also saw that Black women and other women are oftentimes a motivator for a lot of these works in medicine, but they're never really talked about. Like their nuances are never really presented in these analyses, right? So we theorized that we really need to look at those intersectionalities and talk about them in terms of fairness, because some of the things that we're looking for can only be seen when we're looking at intersectionality. Okay, so what we did was we looked at terms that could cause testimonial injustice, such as evidential terms, judgmental terms, negative terms, and stigmatizing terms. Okay, and we took those terms, put them in a lexicon, did a lexicon lookup, count the number of times those words appeared, averaged them out over, the number of visits that some of the patients had to the hospital, And then we set a threshold and said, if they're experiencing at least 10% of the max in any one of the categories of testimonial injustice, then they are experiencing testimonial injustice. And we compared those occurrences to see if somebody's experiencing more based on their intersection through demographic parity, which only looks at either race or gender or age, just one of those aspects, right? So not intersectional. And then we looked at 2 intersectional fairness metrics, subgroup fairness and intersectional differential fairness. All right. And quickly, what the results show is that with demographic parity, it said that there is no bias along race or gender. But when we looked at intersectionality, when we put on our intersectional lens and looked at subgroup fairness, then we saw that out of 112 comparisons, there were 69 violations of subgroup fairness. And when we looked at differential fairness, there were 110. Okay. So these are the main takeaways. If you have any questions for me, then come and find me. Thanks.
Hello everyone, my name is Ankit. I'm a 4th-year PhD student at Harvard, and today I'm going to be talking about decision-focused learning, which is like a technical contribution to maternal health, which is the application domain we're interested in our lab. So just at a high level, I think formatting is weird, but we will continue. The way that often we think about decision making is as an optimization problem. For example, this decision could be who do we allocate resources to, right? And these optimization problems are actually dependent on parameters. And sometimes you assume they're known, but other times you sort of infer them from data. And so this creates a sort of like ML-based decision-making pipeline where you predict parameters and then you make decisions. So a couple of examples here are in route planning, you predict travel times, and then you decide how to route people. Or in wildlife conservation, you first predict where there will be snares, and then you decide sort of like where people should patrol. And so importantly, in the public health domain, we've worked with this NGO in India called EAAMO'23. They have a mobile health program called EAAMO'23, which is very large scale. It has 2.6 million women that it serves so far. And it's basically a very low-tech program. It just gets information that new mothers should have, and it sends, like, it records messages, and then it sends them out to these women. But the issue is women don't want to listen to automated voice messages, and so a lot of them drop out. And what EAAMO' has done to sort of mitigate this is they have health workers on standby who will call these people. But the number of healthcare workers is much smaller than the number of people that they're supposed to serve. And so the question is, how do you get the resources to do it, right? And the way that we frame this is a machine learning problem where you have some information about each of these beneficiaries. You want to predict the probability that they will drop off. And then based on that, you want to make some decisions about who they intervene on. And I guess the key sort of like insight here is that when you're training, you're minimizing some loss function, like mean squared error. But when you're acting, you want to maximize something like decision quality. And these are not, in some sense, the same thing. So what you're training for and what you're evaluating on are different. What does this mean concretely? So for example, in this problem, say you only have the budget to like intervene on 5% of the beneficiaries. So you want to figure out who is at that threshold. So the issue is that mean squared error focuses on getting most of the population's predictions right. And so it actually focuses on like the center of this distribution. When actually what we need to do is we can make errors on the left side of this distribution as long as we get the errors near the threshold right. And so this is an idea that we've been calling decision-focused learning. And the way that we do it is we sort of club the prediction and decision making together, and then we optimize for decision making directly. My technical work, which I will not have work because of limited time, is how do you do this well, and why is this useful, especially in the context of maternal health? Yeah, that's.
Yeah, that works.
No, not.
Okay, all right.
Okay, so very briefly, because the topic of uncovering discrimination is quite complex, but the work focuses on EU non-discrimination law, which has some slight differences with the US law. They're quite beneficial in these world with fairness purposes. But what the task of uncovering discrimination shares across countries, it's usually formulated in a causal way, because we are interested in whether the decision is because of the protected attribute or a cause of the protected attribute. In practice, it often means some sort of counterfactual reasoning, where we try to compare similar profiles of what is versus what would have been, so we can isolate this causal effect of the protected attribute. Nonetheless, it's a non-trivial task, at least in algorithmic discrimination, algorithmic fairness. We use discrimination, fairness, and bias interchangeably, even though these terms are not the same. And there's an overlooked disparity in the field in terms of actionability and meaningfulness of the tool. And by actionability, we mean, are we able to control uncertainty to make a case for discrimination, discriminatory decision? And meaningfulness, are we able to account for at least some recent critiques about what makes two individuals similar or comparable, even though they don't share the protected attribute? So what we try to do in this work is enhance an existing actionable framework with a meaningful objective. So just keep in mind this loan application where you have gender, annual salary, and account balance, and then a bank uses annual salary and account balance. But say we know as a society that gender has a certain influence on these two seemingly neutral attributes. And then we have a complainant C, Clara, that makes a discrimination complaint. So in standard situation testing, we would just recreate the situation of interest by comparing the predicted outcomes of, say, K similar females, which would be the control group, the what is, and K males, the test group, around this complaint. So in practice, it is actually an idealized comparison. So what we do with counterfactual situation testing is we extend the fairness given the difference principle, which I thought the Doctoral critique based on her work. And instead of building the test group on the factual complainant, we do it on its generated structural counterfactual via a structural causal model. So how that looks in practice, if you were to imagine these are all the applicants of consideration, each one representing one, and we can partition the space into membership to be in female and male, so A equals 1 for female. So the red cross would be Clara, in standard situation testing, we would try to find males and females around this distance, defining similarity, and then compare their outcomes. However, if we have this view that, for example, these protected attributes of social constructs that limit the opportunity outcomes of people on the downside, we would say that maybe not the most fairest comparison. Instead, we generate the green dot. It's not in the data, but it's generated. I guess you could call it generative AI. But and then the idea here is once we change the protected attribute, we want every single attribute that has some relationship, i.e., something caused by some downstream effect of the protected attribute to be updated. And then hence you have within group similarity or across group dissimilarity because of this, hence fairness given the difference. And if you have any questions, I'm happy to chat after. Thank you.
Hi everyone, my name is Aziz. I'm a PhD student at Doctoral University. I'm here to present my work in spaghetti bias correction in time code. This is a joint work with my advisor, Vivek, and Vivek Singh and David. So as we all know that machine learning has a problem with the idea sometimes. So basically, the real world is changing and also it's dynamic, it's non-stationary. So basically, in this case, the idea sometimes will be violated. And because in machine learning, we are using a distribution, so this distribution will change over time. And if it does change over time, the algorithmic accuracy and fairness will reduce. So. And one of these cases that we have in machine learning is that maybe the demographic shift. For example, here we have the blue group and the red group, so maybe the red group will change over time. And if you look at the machine learning models, for example, if you have like a binary classification, so you can see over time maybe the red group is somehow associated with the negative class, but the blue group is more associated with the positive. And if you are using the same distribution, the accuracy will drop and also fairness will drop as well. So what we could do is this, we could use the, for example, the temporal aspect that we have in the data set in order to anticipate what can happen in the future, and because of that, we could be like proactive in order to address this issue. So what we have done is basically this framework. So, for example, during the training, we will have, for example, these two time steps, and when we are building the model, what we can do is that we look at the future. And this is the actual future. We could see that the actual future is not present during the training, but what we could do, we could somehow expect it. We could anticipate this future. It looks like similar to the actual future, but it's not correct. It does have some kind of marginal error. But if we are able to anticipate this correlation in the future, what we could do, we could do some kind of correction in terms of the accuracy of in terms of the bias. And what type of correction that we could do before we do the correction, how do we estimate these futures? So one of these aspects we could do is that we could learn from the past in order to predict the future trend, or maybe we could leverage the available data to predict the future. And if we were able to predict the future, what we could do like a pre-processing aspect. For example, we could modify the data representations that we have during the training. We could add some kind of constraint, or maybe we could do like a post-processing where we could just adjust the scores with respect to the expected future. And in conclusion, what we have found is that being proactive will allow us to mitigate the harm before they get amplified in the future. That's it. Thank you so much.
Hi everyone, I'm Johan Naumann, and thanks for still being around. I think we're almost ready for the booster session, so I'll keep this short. I just have one slide, and in the following, let's hope no more than 2 minutes, and gradually going to fill this slide with a very simple generic example in the middle, some buzzwords on the left, and some of the questions that I've been working on and still working on the right side. So suppose we have some data that we use to train a machine learning model, which is used to make predictions of an outcome for people sampled from a population. And these predictions can be, for example, used to distribute some resources or to make recommendations in a population. But keep in mind that a lot of the individuals in this population are different. So let's say, for example, we have a blue group and an orange group, and some for example, the blue group consistently receives unfavorable outcomes and decisions compared to the orange group. So in this example, we can already ask a lot of interesting questions, such as are those decisions fair? How can we even measure fairness in this case? Or maybe also what parts of the system are biased. If we know how we can measure fairness, we can then try to enforce it. We can think about different trade-offs that emerge. To make those decisions more fair in general. However, at this point, let me stop for a moment and think, okay, if we have fair decisions, this is actually what we're after. Because as we know, in many cases, the predictions that we're making for individuals can actually be performative. So this means that the predictions can change the thing they're trying to predict. So in this case, maybe if we're trying to predict whether or not someone will repay a loan, the decision that we're giving them based on this decision can change the probabilities of someone defaulting or repaying the loan. So at the same time, due to those performative predictions, there are a whole range of different types of feedback loops that can be present in the system, which could, for example, lead to self-fulfilling prophecies. So in this case, it's interesting to look at different types of feedback loops and how these feedback loops can relate to biases and whether they could potentially reinforce certain biases over time. And last but not least, another thing that I'm actively looking into at the moment is what if we can't enforce any type of fairness? So what if the decision subjects are not in control and we can't enforce the firm to be fair with regard to a specific metric? Is there any way how we can empower the decision subjects so that they can change the outcomes for themselves and more, so that it's more favorable for them. And what strategy should these decision subject use for that? Would maybe algorithmic collective action be a valuable solution for that? So if you want to know more about feedback loops and how this relates to different types of biases, please check out our talk on Wednesday. If you're interested in anything else that you can see on this slide, come talk to me in the poster session or after that. Thank you so much.
Thank you so much. Hi, everybody. I'm the last speaker, and so thank you all for hanging in there and excited to talk to you about some of the things that I've been thinking about and working on. And so this amalgamation of work is just called Challenges and Opportunities in Data Supported Decision Making. My name is Esme, and I am currently a third-year PhD student at Berkeley. So a challenge that one case study that I've been thinking about is a challenge in these poverty graduation programs or poverty alleviation programs, where oftentimes we're trying to measure some sort of abstract outcome that really requires a lot of different measurements and often noisy measurements of the thing that we actually care about, which is just really hard to measure. And so when it comes to poverty, people try to measure income, savings, consumption, but also try to measure things like material hardship. The number of times a person experiences material hardship, whether they have some sort of income shock, and all of these things contribute to that person's experience of poverty. But in practice, policymakers will often allocate interventions or design new policies based on a single measurement or some sort of like aggregation of these measurements into what's called an index score. And so one challenge that we are trying to address in this line of work is trying to how do we address this in a multi-objective setting. So instead of having to choose one or do some sort of aggregation, can we learn a better representation of these multi-dimensional outcomes? And on top of that, can we learn treatment policies or treatment rules, individualized treatment rules in this multi-objective setting where we have partially observed and noisy outcomes. And so we have a framework for doing that tries to utilize the tools from latent variable modeling and complement, for instance. So yeah, that is one line of work. The second case study that I've been thinking about is this idea of data supported street outreach. So we've been working with a nonprofit who they have outreach workers, a team of outreach workers that goes out and tries to talk to people and help them transition to more stable housing. But they have this limitation in their data where they experience most of the people that they are able to reach and come into contact with are already in transitional housing. And some of them are on the streets as well, and some are in permanent, but as you can see, an oversampling of people in transitional housing. Despite the fact that actually they do have a lot of people on the streets, they just don't have accurate records of them or where they are. And so we're playing with different ways of what you would call this, and I know there's different terms to call it, but this is probably an example of what is called known as survivorship bias, where it's just that the people in transitional housing are just easier to locate. And so how do we address this kind of missing data problem for those in the streets and the more vulnerable population that this organization wants to help. And so that's like one limitation of the data, but the overall goal in this project is again trying to optimally allocate outreach workers to increase successful placements. And so in general, I like to think about these kind of data challenges and how to address them and other questions. So thank you.